Example 8. Melons at a particular fruit store are sold by weight at the price of $2 per kilogram. The masses of melons are normally distributed with a mean of 0.8 kilograms and a standard deviation of 0.2 kilograms. Find the probability that the price of a randomly chosen melon exceeds $2.40. So let's start by understanding what we were given. So we were told that the weights are normally distributed. So let x be the random variable that denotes the weight of a randomly chosen melon. Then we know x is normally distributed with a mean of 0.8 and a standard deviation of 0.2. So what can we say about the mean and standard deviation of the price then? Or rather, what random variable represents the price? Well, for every kilogram that I have in my melon, I charge $2. So 2x will represent the cost of each melon. This is the distribution, the random variable that represents the cost of the melons, 2x's. And this is going to be normally distributed with mean of 1.6. I'm sorry, that should be a 0.2 squared. But what happens to the variance? So here I had 0.2 squared, so 0.04, and then I have to multiply that by 2 squared. So I get 0.16 to be my variance. So what does that mean? And 0.16, of course, is 0.4 squared. So if I want to find the probability the price of a randomly chosen melon exceeds $2.40, that's the same as finding the probability that 2x is bigger than 2.4. And of course, that means that our lower bound is 2.4 and our upper bound is infinity. And we can just go to our GC to find that out. So we'll go to the GC. We look at the distribution. We want the normal CDF. And again, that means our lower bound was 2.4. Our up, why did 2 not come out? Sorry, I'm not used to using a GC on a computer. So lower bound is 2.4. Upper bound is a big number. Our mean is $1.6. Our standard deviation was the square root of 0.16. So what do we get? We get 0.02275. Or to 3SF, that becomes 0.0228 3SF. So what about the next part? Find the probability that 2 times the mass of a randomly chosen melon exceeds 2.4 kilograms. Well, again, that's pretty much exactly the same thing that we just did, right? Where 2x is going to be normally distributed with a mean of 1.6, 0.16 standard deviation. So what do we get? This is the same thing as probability that 2x is bigger than 2.4. We just worked that out. It's the same as before, 0.022823 SF. So part 2, find the probability that the mass of 2 randomly chosen melons is 1,500 grams. So you might be tempted to say, well, 2 randomly chosen melons, that's just the same. 2 randomly chosen melons, you may say that's just the same thing as 2x. But if you said that, I would have to say, no, that's wrong. It's actually x1 plus x2. 2 separate melons, melon 1 plus melon 2. And this is just important for random variables because it shows us that multiplication is not the same thing as addition when we're dealing with random variables. So 2x is different from x plus x. So what do we do? Well, the probability that the mass of 2 randomly chosen melons is 1,500 grams. So I want to know what is the distribution of x1 plus x2, where x1 and x2, of course, are just cases of x, instances of x. So remember, X was normally distributed with 0.8 mean and 0.2 squared as its variance. So this one is going to be what? It's going to be normally distributed with a mean of 0.8 plus 0.8, so 1.6, and a variance of 0.2 squared plus 0.2 squared, so 0.08. And so this is of course in kilograms, so I want the probability that x1 plus x2 is bigger than 1.5 kilograms. That's of course the same thing as 1.5 being less than x1 plus x2 being less than infinity. So we key this into our graphing calculator, and what do we get? So again, normal CDF, and I get 1.5 as my lower bound, infinity again as my upper bound. 1.6 was my mean, and my variance is the standard deviation, sorry, is the square root of 0.08. So what do I get? I get this probability 0.63816 or 0.63823 SF. Part 4. If two melons are chosen at random, find the probability that both of them weigh more than 0.95 kg each. So in this one, we're looking at two separate experiments. Firstly, we take one melon and we see, well, is that bigger than 0.95? And then we take another melon and see, was that bigger than 0.95? Now, these events are obviously going to be independent. Weighing one melon doesn't change the weight of another, right? So that means that I'm just going to multiply the probabilities together. So this is the same thing as asking me, what's the probability that x1 is bigger than 0.95 times the probability that x2 is bigger than 0.95. And again, I can only use times because they are independent events. So what is this? Well, we remember both x1 and x2 come from x, so they're normally distributed with mean 0.8, standard deviation 0.2, so variance 0.04. So we can key this in to our GC. And we're only going to key it in once and then just square it. So I just want the distribution, CDF. The lower bound was negative infinity, right? No, sorry. Oh, the lower bound was 0.95 because we want them to weigh more than 0.95. The upper bound is infinity. The mean is 0.8 and the standard deviation is 0.2. So when we key all of that in, we get 0.2266272794. So I may as well just write that down. Good practice is 0.2266. What was the rest of it? 2266272794 times the same thing, because it's the same distribution, right? And that's going to be equal to, so I'm just going to square that, 0.051359, or 0.514 to 3SF. Sorry, 0.0514 to 3SF. Three melons are now chosen at random. What is the probability that one of them weighs more than 0.95 kg and the other two weigh less than 0.8 kg? So what's this going to be? This probability is equal to the probability, say, that my first melon weighs more than 0.95, and then my second melon weighs less than 0.8, and my third melon weighs less than 0.8. But remember, there's nothing special about the first melon. It could have been the first, second, or third that weighed more than 0.95. So I multiply by 3 to take into account those three permutations. So this is 3 times the number that I had just up here, 0.2266. And then I just have to find out what is the probability that it weighs less than 0.8. So again, I go back to my GC, and I'm looking at a normal CDF, and again, this time less than 0.8 means that my lower bound is negative infinity, my upper bound is 0.8, my mean is 0.8, and my standard deviation is 0.2, but I can already tell you the answer should be a half. Now remember what this mistake that I made before, that should be a little minus sign, not a big minus sign, so there we go. And yeah, this is, it is a half actually. I know it looks slightly bigger there, but if you think about it, it's asked if it wants it to be less than 0.8 and the mean is 0.8, that means that half have to be below it. So this is just a rounding error on the calculator. This should be times a half squared. And when you key that into your calculator, you'll find that that comes out to 0.170 to 3SF. If 10 melons are chosen at random, find the probability that at most 3 of them weigh more than 0.95 kg. So this question's changed a lot now. We're not looking at 1 or 2, we're looking at 10. But if you look at it, we've got 10 repeated experiments, so 10 melons, so 10 repeated tests. And we've got a yes or no outcome with fixed probability. Do you guys remember what this is? This means these are the conditions for a binomial distribution. So actually I'm going to define a new random variable. Let y be the random variable, denoting the number of melons that weigh more than 0.95 kg. Then our number of trials is 10. The probability of success is the probability that x is bigger than 0.95, which I think we worked out up here, right? X bigger than 0.95 was 226627. So this is equal to 0.2266. So what do we do? Well, y then is binomially distributed 10, 0.2266. So I want the probability that y equals to exactly 3, at most 3 of them. So I want the probability that y is less than or equal to 3. So this is just binomial CDF. So I can go to my GC, second function distribution. Maybe going the other way would make a bit more sense. Binomial CDF. And I hope I remember how to do this correctly. This is 10 trials, 0.226627 is my probability, and the number of outcomes I want is 3, and that gives me 0.828 to 3 significant figures, and that is indeed the correct answer. So this is equal to 0.828 to 3 SF. So important here that we don't forget what we've already learnt with the binomial stuff just because we now have normal. Part 6 I'm going to have to do in a separate video, sorry, because I've reached my 15-minute time limit. So any questions on this stuff, please post them in the comments, and I'll go and also do part 6 for you now.